For this first video in section 4.4, I think what I'm going to do is go through and do a lot of the modeling parts of the problems, and then I'll come back in a second or third video, and then we'll come back and do the calculus. So we're just going to go through the setup on these problems, and we'll see how far we get. Question 1 says the sum of two non-negative numbers is 20. So let's start with that. So my two numbers I'm going to use, I'm going to say are A and B, and they've got to be greater than or equal to 0. They're non-negative. Then part A says, actually first, and then it says that we know that A plus B equals 20. Alright, so that's the setup for both A and B. Then part A says it wants us to find the sum of the squares of those two numbers. Find the numbers that makes that the largest. So I'm going to use, doesn't really matter what variable I use. I'll use S for sum. And it says sum of the squares of the numbers. So A squared plus B squared. And so, excuse me, S is the thing I want to maximize or minimize. So step 1 is to write the equation you want to maximize or minimize. Step 2 is to find a way to convert the variables so that I only have one input into my function. So all I have to do at this point is rearrange the equation that they gave us about A plus B equals 20 so that I can solve for one of the variables. So I'm going to make that say, we'll go A equals 20 minus B. And now I can rewrite my equation, and I'll just use all the pretty colors. S equals A is now going to become 20 minus B, the quantity squared, plus B squared. And so S equals 400 minus 40B minus B squared, and let's actually make that plus B squared, plus B squared. So S equals, put in the right order, 2B squared minus 40B plus 400. And now I have an equation that they want me to maximize and minimize. So then when I come back and do the rest of this problem, I'm just going to find my critical values and figure out which ones are max and mins for this equation. So part B then says, let's change colors again. Same setup as before, so we've got the same variables, but this time it says one number plus the square root of another. So I'll use S again, just for the heck of it. So I know that S is going to equal one number plus the square root of the other number. And then once again, I want to make S as large or as small as possible. So what inputs will make S as large or small? So before I continue, I once again need to convert so that I have only one input. So if I go back to the equation I wrote right here, then I get S equals A, which I can rewrite as 20 minus B, plus the square root of B. And this would be the equation, really nothing I can do to simplify that I now want to maximize or minimize. And so now it's time for calculus on that. Okay, so let's move on to number 2. Number 2 says we have a triangle with a hypotenuse of 5, and it is a right triangle. And they would like me to maximize or minimize actually they want me to maximize largest possible area. So the first step is, again, write the equation that you're going to try and maximize. So I know the area of a triangle is 1/2 A times B. And so that's pretty much it. Here's my output. I want to get area as big as possible. What values for A and B will make that happen? Well, once again, I want only one input. So now I got to search for a way to convert an A into a B or vice versa. And so I got to look for another relationship between A and B besides this area equation. In the last question, they had a very explicit statement about A plus B equals 20. In this one, there's nothing explicit said, except we need to gather the information from the triangle. And we, of course, know that A squared plus B squared has to equal 25. And so now I just need to solve for A or B. So I'll solve for A, move the B squared over, take the square root, and I get 25 minus B squared. So now I can rewrite my area equation in terms of one variable. 1/2 A, which is the square root of 25 minus B squared, and times B. And again, there's really not any simplification I can do here. I can bring the 2 underneath, but that doesn't really do anything. So this will be the equation I will eventually come back and do some calculus on. And then question 3 says we have a rectangle and we would like to maximize my perimeter. So the perimeter is the first thing we're going to write. We know the perimeter of a rectangle would be 2 widths plus 2 lengths. And again, that's all I need. I need to maximize this equation, but I need it in terms of one input variable, and I have 2. And so I need to find another relationship between W and L that allow me to convert. And this time they gave me the area of the rectangle. And I know that area equals 1/2 length times width using these variables. And I know then that that has to equal 16. So I have 1/2 LW equals 16. So now I just need to convert. So for no particular reason, I'll solve for W. So I divide or multiply by 2 gives me 32. I divide by L. So I should get a statement of W equals 32 over L, which I can now plug in, giving me the perimeter equals 2W, but W is 32 over L plus 2L. So now I have perimeter equals 64 over L plus 2L. And then I'll come back and this is what we'll do calculus with. Output, 1 input. Question number 4, I think is kind of just the opposite of that question. We have, now we want to maximize the area, and this time we know the perimeter. Actually, looking at it one more time, it says show that among all the rectangles that have a perimeter of 8, that's the biggest one would be the one where W and L are the same. In other words, it's a square. But what it really comes down to is we need to maximize the area and see what we get. So in this case, we have area equals length times width. And again, I'm pretty much done, but I can't have both variables. So now we need to convert. They gave us perimeter. So I have 8 equals 2W plus 2L. I can divide everything by 2, so I have 4 equals 2W. Oh, no. W plus L. And let's just make it say W equals 4 minus L. So I'll use this equation to convert, and I get area equals length times 4 minus length. And let's go ahead and distribute. The area is equal to negative L squared plus 4L. And that I will come back and finish later. Number 5. So I've drawn the picture as best I can. We have this point P Let's start out. We have the rectangle that it's inscribed underneath this curve, meaning that this point is locked onto this line. If we look carefully at this problem, we should be able to determine several things about these triangles. We have a 90-degree angle right here, of course, and we have symmetry here. So we know that, let's see, how do we want to say this? So I know that this length and this length are the same, making it isosceles. If this angle is 90, then this larger triangle, these have to both be 45. And if that's 45 and this is 90, then the smaller triangle, this has to also be 45. So basically what we have is a lot of isosceles right triangles. And that tells us then that this value right here, if this is 1, then that means this leg of the triangle has to also be 1. So we have to be at a height of 1. So part A says express the y-coordinate of P in terms of x. So right now we have it x and y. So what they want me to do is rewrite y in terms of x. Well, y is the coordinate of this point, and this point is locked into this line. So the relationship between x, y is actually the equation of this line. So we should be able to quickly see that the slope is down 1 over 1, and the y-intercept is positive 1. So I know that y is equal to negative x plus 1, y-intercept and negative 1 slope. That's the relationship between x and y. Part B says express the area of the rectangle in terms of x. So I know that area of this rectangle would be, if this is the value x, then this length right here is x, and we would double it because of the symmetry. So we actually have 2x times y, and once again, this is simply the equation we want to maximize, find the biggest area of the rectangle. So we need to convert to one variable, and that's why they helped us figure out that we needed to do part A. So we're going to convert y, and we get 2x times negative x plus 1, or simplified out, and I'll just move it up here for room, area equals, looks like negative 2x squared plus 2x. And part C now wants me to do the calculus and answer the question about the biggest area, so we'll do that later. Okay, so number 6 is a similar question to the last one, except it in some ways is easier because they give me the equation of the parabola. So they told me it was 12 minus x squared. So I sketch the parabola, and again we have this rectangle that is inscribed underneath the curve. And they want me, let's double check, largest rectangle, largest area. So once again, I have area equals, and then let's figure this out. If this length is x, then this length is also x. So I get 2x times the height of the rectangle, which would be the y value. And now I just need to convert into one variable, and we have the equation that relates y and x of the parabola. So that gives me area equals 2x times 12 minus x squared, or area equals, let's see, what are we going to get? 2x negative 2x cubed plus 24x. And this is what they want to maximize. So hopefully you're getting the hang of this. Number 7, we have another open top box like the first example that we did. And we're cutting corners out just like before, so there's no difference here. What dimensions of the box will make the largest volume? So it wants to know my maximum volume, which means I'm going to write a volume equation. Volume equals length times width times height. And we need to convert into one variable, and that variable is going to be x. So we know that we'll say the length is this longer part. So we're going to cut out these little x's out of the corners, leaving me with a distance from here to here of 15 minus 2x's. And then my width would be 8 minus, again, 2x's. And my height would then just be this tab folding up, which would be x. And again, I have my volume equation, and all I need to do now is simplify it out and then do the calculus, which I'll do both of those in the next video. I think I got one more, and then I better move to a new video. Alright, number 9 says we've got a pasture land that has a river on one side, and we have 800 meters of wire to fence in the other 3 sides of the pasture. So I want to know what dimensions I should use so that I enclose the largest area. So we hopefully can easily tell that the area of this rectangle in general will be length times width. And now I need to convert, and I'm going to use the perimeter to help me convert. But we got to be careful, because this time the 800 meters isn't going to go on all 4 sides. We just have to write that the 800 meters is got to be shared with W, 1W, the way I've written it, and 2 L's. And so I think it'd be easiest to say W equals 800 minus 2L. And now I can convert. Area equals length times width. Distribute the L. Area equals negative 2L squared and plus 800L. Alright, so we'll stop here at number 9, and we'll pick up again modeling most of the rest of the equations with the next video.